I am Ángel Ayala, a master student at the Universidad de Pernambuco in Recife, Brazil, and I will present to you our work titled A Comparison of Humanoid Robot Simulators, a Quantitative Approach. I will talk about the inspiration of our work, a brief definition of what is a simulation software, which task was performed to evaluate each simulator, the resource required for the execution of the simulations, and finally, the closure of our work. Implementing a robotic solution is a costly and time-consuming process, where a robot simulator let us evaluate the simulation behavior performance under a controlled environment, avoiding accidents. In development robotics, the robot simulators are widely used to simplify the experimental analysis. There are many simulation tools for different kinds of robots. A large number of mathematical operations must be reproduced in order to reproduce real-world aspects. A simulation requires a determined amount of resource and even a higher amount for a human robot, given the number of joints that must be operated. Previous analysis hardly considered quantitative comparisons. In this work, we compare the CPU, memory footprint, and disk usage during the execution of a humanoid robot navigation task for the Gazebo, Webots, and IEEE simulators. IEEE, since November of 2019, has been replaced by Copelius version 4.0. Many previous works compare the simulators in qualitative aspects, discriminating them between physics engines and simulation systems. The physics engines at the left side of the figure are capable of modeling the physics dynamic systems such as particles or contacts. By the other hand, the simulation systems are there at the right side of the figure are the development environment software, which facilitates the definition of a simulation scene and its development. Another interesting software is the Robot Operating System, which is a framework to develop robot software, isolating how the robot's controller must be operated, being useful to create application programming interfaces and use it with different languages. In our work, we use the Open Dynamic Engine software to evaluate the simulation system, since it has been proven to be the most consistent physics engine. The selected software to comparison are the Gazebo, Webots, and IEEE simulator, for being the best evaluated simulation software in previous works. So for Gazebo, it is an open source software that provides realistic sensor feedback developed by increasing use for robot vehicles. It is designed to reproduce the dynamics of the environment accurately and to be used in a distributed modular architecture, being executed through two processes, where one is the server and the other one is the client. At the right side, we have the Gazebo 3D shaped scene for our task. Webots is a software which has become open source recently, since December 2018. Presents an easy-to-use and friendly interface to model, program, and simulate robots. And additionally, it can compile the source code of the robot's algorithm inside its interface, making it possible to test and validate the algorithm quickly. IEEE is the generic robot simulation software that allows embedding controllers and functionality into simulation models in different programming languages. It presents a broad models library that can be useful to develop a scene in just a few minutes, considering the environmental elements and the robot itself, being widely used in both the academic and the industrial fields. To evaluate the simulation requirements, we choose the now humanoid robot to perform a navigation task where must reach a goal position. This must avoid an obstacle in between. This task was executed 20 times for each simulator in order to obtain statistical measurements. During the task execution, the now must go around a chair, which is considered the obstacle to reach the goal position, as can be seen here at the image. These tasks let us evaluate the simulator under many turns and movements made by the robot. In this way, we can measure the workload required by each simulator to perform the tasks in terms of CPU, memory footprint, and disk use. Now is a human robot used mainly for education and research purposes. It was developed in 2008 by Aldebaran Robotics, which now is a Software Robotics Group subsidiary company. Presents the ability to perceive the environment from a broad kind of sensor like cameras, microsoft, and tactile, among others. Also includes expression elements like 53 RGB LEDs, possess a voice interfaces and 2 speakers, which gives a high degree of interaction. Support a variety of programming language to configure its behavior, and additionally, the choreograph software allows interactive action programming using a flow diagram. It can work online with the robot's hardware, keeping dialogues and capturing the element recognized through its camera. To measure each evaluation component, we use a GNU Monitor System, which is a software capable of obtaining information about the resource and used by a process in execution at every moment, the current CPU and memory used visualizing in real-time graph, and the occupied hard disk space. Also, the IO-Top Monitor is a software which provides information about the existing disk usage by a process or a sub-process in the system, and is useful to track those processes that present a high read-write operation in the hard drive unit. All the simulators were configured in a VirtualBox version 2 virtual machine, set up with a Intel Core i5 at 2.3 GHz, 6 GB of memory, and a hard drive Hitachi SATA 2 at 7,200 revolution per minute hard disk drive. The selected OS was Ubuntu 18.04, due to its broad community support and compatibility with the simulation software and BOS. The now behavior was executed by each simulator separately to measure each evolution component. Each component presents the same impact in the overall comparison. Also, with this, we mean that all the components are equally weighted. So, in terms of CPU load, as can we see in the figure, we would achieve the lowest mean value with 11% of use, followed by VREP, which use almost twice of CPU with 20%, and finally Gazebo with 42% mean CPU use, as can we see in the figure at the right. Now in terms of the memory footprint, which is represented in megabytes, the bird simulation achieved the second best with an average of 212 megabytes, which put with a stable memory requirement. Opposite observation can be observed for Webots and Gazebo. Nevertheless, Webots achieved less variation in memory with an average of 176 megabytes requirement between each execution than Gazebo, which present an average of 203 megabytes. So with in terms of disk usage, presented as transaction allocated for disk read-write access. All the simulation requires a low amount of disk transactions. However, Webots require almost no disk usage with a mean disk use of 0.12%, followed by Gazebo and VREP with almost 6% and 8% respectively. Summarizing the results of the 20 execution, we can observe in the figure that both CPU and disk usage have a remarkable variation among simulators. It can be interpreted that Webots can simulate efficiently considering the non-existence of the hard disk access bottleneck and the fewer CPU load, which is in between of 10 and 12%, and memory requirement, which is between 170 and 180 megabytes. In comparison, VRAP requires more CPU and presents a higher disk usage. However, the memory footprint is stable over all the runs. And finally, Gazebo is the simulator that requires the most resources but requires less disk usage than VRAP. So as conclusion, robotic research presents a high computational cost in its development to ensure the feasibility of its implementation in real-world scenarios. In this work, we compare the Gazebo, Webots, and VRAP simulation system, evaluating the CPU memory footprint and disk access during the execution of a navigation task performed by a now humanoid robot. The compared simulator presents similar qualitative characteristics like the programming language interfaces, the use of all the physics engine, and the capability to control the robot externally. The quantitative results show that we would obtain the best score in simulating the now robot, requiring fewer resources. However, VRAP presents a stable use of memory and a large repository of simulation models. Finally, Gazebo requires almost the same amount of resources considering the use of two processes. Future research directions can consider other metrics like time, different physics engines, or another simulator. Additionally, some different scenarios or tasks can be considered where other aspects are involved, like path planning, reverse kinematics, and collision avoidance. Moreover, for a fair comparison can be considered different weights between each evaluated component and also include qualitative aspects. Thank you for your attention.